Welcome everyone to Session 3 of the Immunisation Coalition's 2022 Annual Scientific Meeting. This session will be discussing COVID-19 theory versus reality, and we have three fabulous speakers to discuss this topic. Firstly, I would like to acknowledge the traditional custodians of the various lands on which we work today and the Aboriginal and Torres Strait Islander people participating in this session. I pay my respects to elders past, present and emerging, and celebrate the diversity of Aboriginal peoples and their ongoing cultures and connections to the lands and waters of Australia. Before we start, some housekeeping. All sessions will have a similar format. We'll have three presenters who will each present on their topic for 15 to 20 minutes. At the end of the third presentation, we'll have 20 to 25 minutes for panel discussion. Our first speaker this morning is Dr. Jennifer Juno, who will discuss COVID immune response. Jennifer is a T cell immunologist currently working at the Peter Doherty Institute for Infection and Immunity. Jennifer leads a team focusing on harnessing specific T cell subsets to improve immunity against human infectious diseases. Jennifer, welcome to the session. We look forward to your talk.
Great, thank you so much for the introduction, and I'd like to thank the organizing committee for giving me the opportunity to talk today. I think it's an interesting challenge to try to cover what we know about COVID-19 immune responses in a 20-minute talk. But in other ways, at the same time, a lot of what we know can be summed up sort of in one slide here. And I like to start by showing this figure from a recent review from Shane Crotty's group that really summarizes what we understand about the immune response to mild or moderate SARS-CoV-2 infection. And that's characterized by very typical antiviral immunity. So early on, we see the activation of the innate immune response as viral loads begin to increase. And then over time, we see the recruitment and initiation of the adaptive immune response. And that includes the production of antibodies, as well as the elicitation of T and B cell responses. And ultimately, these protective immune responses are able to constrain viral replication and lead to the clearance of the virus and the resolution of the infection. And there's been so much work done over the last 2 years, really aimed at understanding the protective components of this immune response and when things can go right and when things can go wrong. And so initially, early in the pandemic, we were really focusing on understanding adaptive and innate immunity to SARS-CoV-2 infection. And the goal there was to try to identify some correlates of protection, so what makes a protective and good immune response, and also to understand what mediates disease severity and understand what might be the failure points when something goes wrong. And now, of course, more recently, we've also moved into an understanding of COVID-19 vaccines that are available. As the global rollout, and especially here in Australia, has moved forward, we've started to ask more questions about the durability of the immune responses that are elicited by these vaccines, what the impact is of boosting and how that can change our level of protection. And of course, more recently, really trying to understand the impact of different viral variants as they emerge and spread around the world. And of course, particularly with Omicron in the recent months. And finally, I'll talk a little bit at the end of our talk about some data that we've been looking at with breakthrough infection. So trying to understand what the immune response is like when someone is vaccinated but then does become subsequently infected, and how that might differ from the immune response to a primary infection or the immune response to a vaccine. I just wanted to start, though, by talking about the antibody response, because, of course, when we talk about immunity to infection or immunity from vaccination, typically we're always talking and focusing about antibody responses. And on the left here, I've just shown a little schematic of the SARS-CoV-2 spike protein, and in particular highlighted the receptor binding domain. And this is the portion of the spike protein, of course, that binds to the host receptor, ACE2, and is what allows the virus to attach to our cells and initiate an infection. And so we're particularly interested in antibodies that target epitopes within the RBD or near the RBD, because these are the antibodies that are able to neutralize the virus. So they can actually block binding between the spike protein and the ACE2 receptor, and it's these antibodies that can really prevent an infection from occurring. And we'll talk in a couple of minutes about how mutations within these regions, especially within the RBD and the surrounding areas, can affect the ability of antibody responses to actually recognize the spike protein, and why this is really important within different viral variants. Now, the development and the understanding of antibody responses to the spike has been incredibly important in our development of therapeutics against SARS-CoV-2, and that includes the development of a number of different monoclonal antibodies that are able to be administered to individuals who maybe don't make enough of their own antibody response, and to try to mitigate viral replication and mitigate disease severity. And of course, the spike protein is particularly important because a number of our currently approved vaccines target the spike protein, in particular the mRNA vaccines and the AstraZeneca vaccines that express only the spike portion of the virus. And really the goal of these vaccines is to elicit high titers of neutralizing antibodies, in addition to B and T cell responses, to provide protection from infection. And the reason that we focus so much on neutralizing antibodies is because we now understand that these neutralizing responses are really the best correlative protection that we have for infection or symptomatic COVID-19 disease. And this figure here I wanted to highlight comes from some recent work out of New South Wales from Miles Davenport's group. And they looked at the relationship between the efficacy of different vaccine platforms from phase 3 clinical trials and the neutralizing antibody level that each of those vaccines elicited. And as you can see, there's a really nice relationship between the neutralizing antibody levels elicited by each vaccine and their protective efficacy in clinical trials. And they were able to use this relationship to develop a model that would actually predict vaccine efficacy based on neutralizing antibody titers reported in preclinical studies. And since that paper came out, it's been really effective actually at predicting the vaccine efficacy of other candidates that have since reported in their clinical trials since that paper was published. But this isn't the only data that we have to suggest how important neutralizing antibodies are as a correlative protection. There's been some really nice work done in animal models as well. And in this particular study that I'm showing here, there were mice that were infected with SARS-CoV-2, and after they recovered from their infection, they transferred either the serum or the T cells from those mice into recipient mice and then reinfected them. And as you can see, it was the mice that received the serum, so the mice that received the antibody components, which were protected from reinfection. So again, we have this nice mechanistic evidence as well, suggesting that neutralizing antibodies are really key for protection from infection. Now, of course, that brings us to the observations that have been widely reported, which is that the neutralizing antibody titers, whether they're elicited by vaccine or by infection, do start to wane over time. So what do we know about these neutralizing antibody responses? Well, we reported early last year in a cohort of individuals with mild and moderate COVID-19 that there was a very large amount of diversity in the neutralizing antibody responses that were elicited by infection. So some individuals in our cohort on the left here had almost undetectable neutralizing antibody activity after they recovered from their infection, while other individuals had much, much higher titers. So there is a lot of diversity in the level of immune response and the level of immune memory that we can see in individuals after they recover from infection. Now, the really nice news is when we started to get data on our vaccines, we saw that vaccines were particularly effective at eliciting neutralizing antibodies. So compared to infection, the neutralizing titers from some of the mRNA vaccines, as well as the recently authorized Novavax vaccine, do a much better job than infection at eliciting high titers of neutralizing antibodies. And that's part of the reason that these vaccines have been shown to be so effective, at least initially. What we find, however, though, is that regardless of how you see the virus in the first place, whether you see it from an infection or whether you see the spike protein from a vaccine, antibody responses in the blood seem to wane at similar levels. So we followed up a cohort of convalescent individuals after their infection for about 4 to 5 months, and we found that the neutralizing responses first declined relatively quickly and then stabilized, but still continued to decline over time. And this is similar to other analysis that is shown after vaccination or after vaccination and infection together, that these neutralizing responses continue to wane at relatively the same rate. So that is then further exacerbated by the fact that we now see the spread of new viral variants, and in particular Omicron. And these variants can have a dramatic impact on our ability of our antibody response to actually recognize the virus. There have been a number of studies that have come out recently. One in particular is shown here, where they looked at plasma samples from previously infected individuals, vaccinees, or vaccinees who had received a third vaccine dose, and they looked at the ability of that plasma to neutralize either the original wild-type-like virus variant or the Omicron variant shown here in the red. And what you can see is that very consistently, again, regardless of how immunity was established, that there was very poor ability of our antibodies to recognize the Omicron variant. And this has had many clinical implications as well. A number of the monoclonal antibodies that were approved for therapy that target different portions of the RBD are also affected by the Omicron variant, and they can no longer bind. And this has really reduced the number of options that are available for therapeutics from the monoclonal antibody space for Omicron infections. So what do we do in this case? And we're faced with waning immunity from infection and from vaccination, as well as new viral variants. How do we want to establish a long-term level of immunity against SARS-CoV-2? And there are a couple of options here, which are playing out interdependently right now. The first is to try to maintain protection from infection. We probably need to use repeated booster vaccines. It's the only way to really maintain high levels of neutralizing antibodies within the blood. Otherwise, they are going to wane over time. And we've already seen a lot of data, and I'm just showing one example here of how effective the booster vaccine is at restoring neutralizing antibody titers to their original or potentially higher than their original levels when boosters are given 6 to 7 months after initial vaccination. And I'll talk about some additional data from our studies later defining the immune response to extra doses. Additionally, however, if we're really concerned about protection from severe disease and protecting people from hospitalization and death, we're really likely relying on long-term memory from B and T cells to remember the SARS-CoV-2 virus and initiate a recall memory response. And I want to talk a little bit about the T cell response to SARS-CoV-2. As a T cell immunologist, I very much appreciate the antibody responses, but I also want to highlight various ways in which the T cell response can contribute to our immunity. And so T cells can act in a number of different ways to influence the immune response and to potentially contribute to protection from COVID-19. The first is through Cd8 T cells, which are also commonly referred to as cytotoxic T cells. And these cells are able to recognize a variety of different antigens from SARS-CoV-2, not just the spike protein. And that recognition allows them to kill and eliminate virally infected cells. And obviously this can be very important, particularly in the control of viral replication and hopefully the mitigation of severe disease. Additionally, both CD4 and CD8 T cells can support the immune response by producing antiviral cytokines such as interferon gamma and TNF-alpha. And finally, CD4 T cells can play a very important role in the production of antibodies. So we don't just need B cells in order to produce a strong neutralizing antibody response. We also require a specific subset of CD4 T cells called T follicular helper cells. And these cells are really key in promoting a strong and robust neutralizing antibody response. So there are many different ways in which T cell responses can actually promote the immune response to COVID-19 and hopefully protect us from severe disease. So what do we know about the T cell response elicited by either infection or vaccination? So we've been doing a number of studies looking at CD4 T cell responses. And in particular, we've developed a reagent, an MHC class II tetramer, that allows us to directly identify and track spike-specific CD4 T cells over time. So you can see these cells here. And what we find is that following primary SARS-CoV-2 infection, these T cells expand in the peripheral blood about 34-fold. So we see a really strong response of these cells to the spike protein. And what's really encouraging is that we're able to track these cells in the blood over time. And of course, initially after infection, we do see a decline in the frequency of these cells in the blood. But between 6 months and 1 year, we see this really stable population of cells, suggesting that there is a really long-lasting CD4 T cell response. And a number of these individuals we followed out for more than 15 months after their initial infection. And you can still see that we can detect levels of these memory cells specific for the SARS-CoV-2 spike protein. Similar studies have been done looking at Cd8 T cells. So we know that the Cd8 T cell response is able to target a wide variety of antigens. So like I said, it's not just restricted to the SARS-CoV-2 spike. It can also recognize other proteins from the virus. And these cells that are elicited by infection express all the right cytolytic molecules and should be very capable of killing and eliminating infected cells. And again, similar to what we find with the CD4 T cells, we see that these responses are relatively stable over time, and we think that, again, a nice stable population of these memory cells is formed following infection. Now, the key thing, and potentially the really useful thing about the T cell response to the virus, is that there is not as much of an impact of variants of concern on the T cell response compared to what we see with an antibody response. So the antibody response for the neutralizing antibodies is very constrained, because those antibodies need to recognize specific portions of the receptor binding domain in order to be able to neutralize the virus. And as a result, mutations in that area can really impact their ability to bind to the spike. However, there are a number of T cell epitopes all throughout the spike protein, and as a result, the mutations that we see in variants of concern have less of an impact on the overall T cell response. So last year there was a number of studies that came out showing that the T cell response across the original Wuhan strain, alpha, beta, and delta were all conserved. And more recently this year we've also seen similar data now showing that the T cell response across Omicron is conserved as well. So although there may be an impact on the antibodies being able to recognize these variants of concern, we expect that T cells will continue to be able to recognize the majority of variants that might emerge into the future. Now, how do our vaccines do at eliciting a T cell response compared to infection? Well, again, we were able to use our tetramer and our vaccine cohorts to compare the frequency of spike-specific T cells elicited by mRNA or AstraZeneca vaccines compared to infection. And we see that they elicit really similar frequencies of cells, actually. They have a similar phenotype, similar frequency, and overall, they seem to be a very comparable response between infection and vaccination. And when we track these cells over time, again, we can see that even the first dose of vaccine, in this case the Pfizer vaccine, was capable of eliciting a T cell response as early as about 7 days after the first dose. And then the second dose further boosts these cells, which again are maintained at very nice memory frequencies out over time. Similar studies have been done looking at the Cd8 T cell response, and although the Cd8s don't tend to be elicited quite as strongly as the CD4 cells, again, we see very good elicitation of Cd8 T cell responses that express all of these nice cytotoxic molecules that we would expect to be required for killing and eliminating infected cells. One interesting thing to note is that in studies over time, although both the CD4 and Cd8 T cells remain detected for about 6 months after vaccination, it seems that the CD4 T cell response is a little bit more stable. There's a little bit of evidence for a greater waning of the Cd8 T cell response compared to the CD4s. And of course, as time goes on, we'll have longer studies following vaccination out, even out to a year or 2 years, and we can start to get a sense of how durable these responses are going to be. Now, most recently, we've had the opportunity to compare our data from our 2-dose vaccine cohort to a booster cohort to try to understand how the immune response to the 3rd dose actually compares to the original 2-dose schedule. And so the first thing we looked at was the antibody response. So I'm showing here the spike-specific antibody response after the 2nd dose of vaccine, and then about 6 months later, pre-3rd dose, and then following the 3rd dose. And what was really interesting, and this is consistent with data from other groups, is that the 3rd vaccine dose actually elicits antibody responses that are significantly higher than what we saw after the peak of the 2nd dose. And so not only are we restoring the immunity that waned over time, but we're actually getting a better immune response to dose 3 than what we saw to dose 2. And this is borne out by the neutralizing antibody responses as well. You can see following dose 3, we get significantly higher responses than we did after the first 2 doses. And these responses are quite comparable, actually, to what we see in cohorts of people who were infected and vaccinated, which is often called hybrid immunity. And so these seem to be 2 situations in which we can get really nice, high levels of neutralizing antibody responses. What's striking, though, I think, is that the T cell responses were a little bit different. And while we did see waning of the T cell response over time, it was restored by the 3rd dose, the 3rd dose actually just brought the T cell responses back to their original level after dose 2. So we didn't see that extra enhancement that we saw with the antibody responses. And this just points to some subtle differences between the B cell and T cell responses to the 3rd dose of vaccine. However, it's very nice to see that the booster dose did restore the T cell frequencies back to what we got after dose 2. We also tracked the kinetics of these responses to try to understand how quickly the immune response was able to be boosted by this 3rd dose. And again, we saw some striking differences between the T cells and B cells. So when we look at T cell activation after the 3rd dose, we find that it was peaked and was maximal around day 6 post-vaccination, at which point it then declined as the cells sort of returned to a resting state. But interestingly, the antibody responses were a little bit different and a little bit slower. So what we saw was that the peak of the antibody responses occurred around day 10 to day 12 post-vaccination, but they were very nice and stable over the 1 month of follow-up. So again, suggesting that we see differences in the recall of T cells and B cells to this third booster dose. Now finally, I just wanted to highlight a little bit of very new data from our group looking at the impact of a breakthrough infection on immunity. So we recruited a cohort of individuals who had been previously vaccinated, but then experienced a breakthrough infection at the end of 2021. And this was during the time when the Delta wave was most predominant in Melbourne. So these were not Omicron cases. And we wanted to track and understand how quickly their immune system responded to this breakthrough infection. So we obtained longitudinal sampling from some very dedicated cohort participants, which was daily in some cases from the day of symptom onset. And we had both nasal swabs and blood samples. And really nicely, the precise date of exposure was actually known for 2 of the cases, shown in the red and the yellow here. And these data are just showing the PCR results from their nasal swabs, and you can actually see the increase and then decrease in viral replication over the course of the breakthrough infection. So what we saw, first of all, was quite interesting. We did see in all of the individuals a boost to their neutralizing antibody titers. So the infection did actually act in a way like a vaccination and improved their neutralizing antibody titers over time. This didn't occur quite as quickly as we expected, though, particularly in the individuals with daily sampling. We found that this didn't really take off until about day 7 or day 9 post-symptom onset, so it's a little bit delayed compared to the kinetics that we saw with our 3rd dose vaccine cohort. We also saw that the memory B cells, so these are the B cells that are circulating in the blood and remembering the virus for exactly like this, re-exposure to the virus, do start to increase in frequency, but again around day 9 or 10 after symptom onset. And then really surprisingly, when we looked for reactivation of the T cell compartment, we actually found that only 1 individual really showed convincing evidence of T cell reactivation. And so we're not sure if this is specific to Delta virus reinfections, if this means that these infections were sufficiently mild that the T cell recall didn't actually have to occur. But there are a number of questions that we want to look at regarding why we didn't see reactivation of T cells in these individuals. And so finally, when we put this data together, I think the most striking thing is that when we look at the viral replication, shown here in blue, compared to the antibody responses shown here in red, we can see there seems to be this nice parallel concurrence between the decrease in viral replication and the increase in the neutralizing antibody response, suggesting that, again, antibodies may be one of the most important correlates of understanding how we can control viral replication. So there are a number of questions that we're still ongoing with the study, including understanding how these breakthrough infections would differ between Omicron and Delta, whether the T cell recall would increase in individuals with greater disease severity, and also how we can predict the severity of breakthrough infection based on pre-existing immune responses. So with that, I'll just wrap things up. I just want to highlight that overall, when we talk about the immune response to COVID-19, we're talking about a number of different components that are working together. So antibodies and memory B cells that seem to be really important correlates of protection, Cd8 T cells that are important in supporting the B cell response and producing antiviral cytokines, and also the Cd8 T cell response, which can lead to killing of infected cells and potentially impact on disease severity. And with that, I'll wrap up. I'd just like to thank the individuals who contributed to this. It was a really large team effort, and I look forward to taking any questions in the panel discussion later. Thank you.
Thanks, Jennifer. A terrific discussion about COVID immune responses. Our next talk is on the very complex subject of disease modelling, and Dr. Patricia Campbell, who's also from the Doherty Centre, is going to give us a 101 on modelling. Trish, I'm really excited to learn more about modelling. Thank you for your talk.
Thanks for inviting me to present today, giving a brief introduction on modelling, particularly in relation to COVID. I'd like to begin by acknowledging the traditional custodians of the land from which I'm joining today, the Boonwurrung people of the Kulin Nation, and pay my respects to their elders past, present and emerging. So what are models? When we're talking about models that we use for infectious disease, we're talking about something that's a simplified representation of the world. It's not as complicated as the world. And we build in the mechanistic processes by which disease spreads in populations so that we can better understand the patterns of disease and how they're going to spread and how we can control them. So we identify a problem, we ask a question, we collect the data so that we can understand the system, we choose the best type of model, and then we examine scenarios and compare them to see what might happen if we take particular actions. So you may well have already heard of the classic SIR model, Susceptible Infectious Recovered Model, because it's been around for almost 100 years now. It forms the basis of most infectious disease modelling today, and it works on the premise that we can divide the population up into compartments based on their disease status alone. So we can split a population into susceptible people who can be infected, infectious people who can infect others, and recovered people who can neither infect nor be infected by others. So they're essentially removed from the transmission process. And the idea of this model is that everybody in a population is exactly the same except for their disease state. So we start with a population of individuals who are exactly the same, and we split them into susceptible people, infectious people, and recovered people. And then because they are all the same, we can then just group all of those people with the same status together. So we can count how many people are susceptible, how many people are infectious, and how many people are recovered in our population. In the model, we consider the events that cause individuals to change the state they're in. So people change from being susceptible to being infectious if they become infected. So the event is infection. And people who are infectious become recovered if they recover. So the event here is recovery. And we use differential equations to track how the population in each of these compartments changes. So our susceptible compartment decreases by the number of people who are becoming infected. Our infectious compartment increases by the number of people who are becoming infected, but it decreases at the same time by the number of people who are recovering. Our number of recovered people is increasing all the time by the number of people who are recovering. The classic SIR model is quite simple, it's easy to understand and to apply to a population, but it's not that realistic when it comes to modelling typical diseases that we see in populations today. So we almost always have to add additional complexity to this simple model to match what's happening in the real world. So for example, age is often a key indicator of susceptibility to infectious diseases. So we often want to stratify our model into different ages. So we repeat our model compartments for different ages. Or it might be really important to split our population into asymptomatic people and symptomatic people. If, for example, we expect asymptomatic people to be less infectious. And the type of immunity that people have might be important as well. If people have immunity due to being vaccinated compared to immunity due to being infected, we might expect to see different outcomes. So all of these complexities can be added to the SIR model. I mentioned at the beginning that we collect data when we want to build transmission models. So what do we actually need to build them? We need information on the natural history of a disease. So how transmissible is it or infectious? How long are people infectious for? How long does it take before people show symptoms once they've been infected? And can they infect people before they show symptoms? What population are we modelling the disease in? So how big is it? What's the age distribution of the population? And do we have treatments or other interventions for the disease? So such as vaccination. And what's the action of that? Does it reduce susceptibility to infection or does it just make the disease less severe? So these are all sorts of information that we collect in order to build a model so that we can understand how quickly people move from one compartment to another compartment. Throughout the pandemic, you might have heard a number repeated quite a lot called the effective reproduction number. The effective reproduction number gives an indication of how quickly an outbreak can grow or how it's going to decrease, for example. So it's defined as the time-varying expected number of secondary cases that a typical infected person will cause in a population that is not fully susceptible to infection. So in this diagram here, what we can see on the left, we have an effective reproduction number that's greater than 1. On average, everybody is infecting more than one person. So our epidemic is growing. Our number of people is increasing. In the middle, our effective reproduction number is equal to 1. So everybody is just replacing themselves so that when they recover, the number is staying exactly the same. On the right-hand side, we have an effective reproduction number that's less than 1. And so people on average are infecting less than themselves, so that when they recover, the number of people who are infectious in the population is reducing. And we call that containment. So that's what we're aiming for. I'm going to just briefly touch on 2 examples of the Doherty modelling that's been done for COVID-19 in Australia. We're going to start back in early 2020, before we knew much about COVID-19 at all. So we did some preparedness modelling. This was done by Rob Moss and colleagues at the Melbourne School of Population and Global Health. So you can see here, this is a transmission model that Rob Moss developed that tracks how people move through the system. And you can see some of those common compartments, the S, the I and the R compartments. But we've also made it substantially more complex than it was previously. We now have people who are infected but not yet infectious in an exposed compartment. We have people who are infectious but not yet symptomatic. So they're spreading disease but we don't know they're infected yet. We split the population into people who are quarantined, so that people who are infected when they are quarantined are less infectious than other people. And we also split the population into people who isolate when they are identified as a case. And these people don't contribute to the risk of transmission at all anymore. So what we do with this model is we start from a starting point of a susceptible population, and we run it over time with all of those rates that we have of how people move between compartments. And we generate from that a daily presentation numbers split into mild and severe manifestations. And we then take those numbers and we run them through an additional model shown here, which is called a clinical pathways model, where we're looking at the way that mild and severe cases utilise healthcare. So how people present to emergency departments, whether they're going to need hospital beds, whether they're going to need ICU beds, and what happens if when they need those, they're not available. So we have rules built into this clinical pathways model, so that when we've run this, we end up with a daily usage numbers for each healthcare channel. So how many people need on a given day emergency department, ICU beds or hospital beds. And from that, we can then present a time series of how these items change. So here, these plots show the daily demand for ICU beds. In the top plot, what we're seeing is a COVID-19 outbreak unmitigated. We're taking no action whatsoever. The red line here is the median one, so we'll just focus on that. That's an average simulation, produced around about a peak of 400 daily ICU beds required. In the bottom plot, we look at what happens if we institute case isolation, so that's those people who are no longer infectious because we know about them, and we also quarantine people's contacts. And so we're seeing that we can reduce the number of ICU beds required, so down to about a peak of 200. So in this way, we can have a look and see and better understand what it might take to flatten the curve so that our experience with COVID-19 falls within our healthcare capacity. So now we're going to fast forward to mid-2021, when we've experienced a few waves of COVID, and now we want to transition Australia's COVID response from a suppression phase to a living with COVID phase. Unlike the preparedness modelling, which used the compartmental models that I previously described, the transition modelling used an individual-based model. With an individual-based model, we don't group individuals by status, but we explicitly model their characteristics. So instead of counting up how many susceptible people, infectious people and recovered people we have, we keep them as individuals. And now we, as well as knowing their disease status, we know how old they are, what vaccine they had, so AstraZeneca, Pfizer, how many doses they've had and when that was, Have they been infected and when that was? So we have a detailed history of all of the individuals in the population. And it's this fine control that we get by keeping people as individuals that mean that we can implement quite detailed vaccine implementation within our model. And we can also efficiently identify cases and quarantine their contacts and isolate the cases. So in this particular model, the effect of vaccination is to reduce susceptibility to infection and reduce infectiousness if infected. Also reduces the probability of symptomatic disease. And there were 3 different vaccine allocation scenarios considered, where we vaccinate the oldest people in the population first, or we vaccinate people older than 40 first, or we vaccinate all adults with no given preference. Our transmission, we have age-specific susceptibility, so some ages are more susceptible to infection than others, and people will have varying probabilities of developing symptoms given infection. Asymptomatics are less infectious than symptomatic people as well, as I alluded to earlier. The simulations were run with a Delta type variant, and the epidemic is seeded. We introduce infectious people when either 50%, 60%, 70% or 80% of the population is vaccinated. We continue vaccination as the epidemic takes off, so that we keep increasing the number of vaccinated people in our population. We assume that there is some partially effective test, trace, isolate and quarantine in place, similar to Victoria's second wave. The output of this model is a line listing of each individual who got infected on a particular day, what their age is, their vaccination status, how many doses, what type of vaccine they had, and their symptom status. And from this, we can generate daily case numbers and again feed into a clinical pathways model. One of the questions that we wanted to answer with this model is, what are the levels of interventions that we need to be able to control Australia's COVID epidemic in the event that it's going to continue? So we're talking about Delta, so we're talking about a relatively high effective reproduction number to begin with. And what we want to know is, what do we have to put in place that's going to bring that number down to 1 or below? So each of these bars here represents a different level of vaccination coverage, ranging from 50% on the left to 80% on the right. The pink bars represent a standard baseline implementation of public health and social measures, such as staying 1.5 metres away from each other, for example, and that partially effective TTIQ response that I mentioned earlier. We look at what the effect of that is on our effective reproduction number, or transmission potential as we're referring to it here. And then we add the effect of vaccination. And we can see that even with 80% vaccination, we still can't get below that 1 effective reproduction number. We need to add some additional public health and social measures to achieve that number 1. So this might be things like having capacity limits on our venues, or going to the high public health and social measures, no household visits, work at home, stay at home orders in place. So this is a way for us to inform policy about what we need to do to safely open up. So these are just a couple of examples of what we've done to show how mathematical and computational models for COVID have helped us to understand what we might have to put in place to be able to minimise the consequences of COVID transmission. COVID is a rapidly changing situation though. We're having new variants all the time and seeing different responses to vaccines, different capabilities of vaccines. So we need to continually update the models as new information becomes available, either from the Australian experience or the overseas experience. The models described here represent what-if scenarios. So what if we implemented a particular strategy? What would happen? What could happen? They're not predictive models, and we would caution against using these models for more than a month out from when they're designed, because things do rapidly change. So they give you a list of possibilities rather than a prediction of what's going to happen. Now, this work has been done by a large team of modellers from across the country, from a number of different institutions, and I've mentioned those people here. So thank you very much, Lou, for the opportunity to present this work.
Thanks, Trish, for a terrific introduction to modelling. And this will help us actually follow the next talk, which is what's actually happening on the ground, predicted by modelling and despite of modelling. And this talk will be given by an old friend of the Immunisation Coalition, Professor Alan Cheng. Alan hardly needs an introduction, but he works at the Alfred Hospital as Director of the Infection Prevention and Healthcare Epidemiology Unit, and has also been one of Victoria's Deputy Chief Health Officers during the COVID-19 pandemic. Alan, welcome, and thank you for talking to us today.
So thanks very much, Lou, and thanks for the invitation to speak at the Immunisation Coalition again this year. I'm taking up from where Jodie left off. This is being pre-recorded, so I haven't had the privilege of seeing what she's said, but hopefully this fits in relatively well. And what I'm going to talk about is modelling from the side of the policymaker. So how are models used, and what do governments look for in models? So obviously I was Deputy Victorian CHO for a year until June 2021, and I was involved in the Victorian Roadmap policy, but not in the commissioning of models in 2020, and that was the Department of Premier and Cabinet. And I haven't been formally involved in Victorian policy since I left the department. And I am a member of HPPC and was the co-chair of ATAGI until December. So what I'm going to say today is really about modelling being more like a quantitative thought experiment than a prediction. Models, when you're commissioning models, you really need to be clear on what exactly are you asking, and how are you interpreting what you get back. And in particular, you need to be very careful about avoiding the illusion of precision that you can get from numbers. For policymakers, you need to consider, what assumptions have been made, what things we don't know that might be really important, and you can model anything you like, but you want to make sure that what is modelled is, in terms of an intervention at least, something that's feasible, and you need a bit of reality checking to make sure that what you're seeing is what you think the real world does look like. And then unknown unknowns will always change the game, and there will always be unexpected new pieces of data or new variants, as the case may be. And then finally, governments do expect and want different things to academics. So the example I'm going to give is the easing of restrictions during Victoria's second wave, and really the thinking was that we got to the point of imposing stage 4 restrictions, and that really started to turn the tide on the case numbers that we were seeing in about August 2020. But just before that, there had been stage 3 restrictions and masks, and that had probably reduced the effective reproductive ratio to about 1, or maybe just a little bit below 1. In general, the tighter the restrictions, it meant the shorter that they would go on for. And the aim was really that we wanted broad restrictions that basically would reduce the amount of contact people had with each other. And so that were things like limitations on movement, stay-at-home directions and the curfew, the limits on gatherings, and then having a list of authorised or permitted workplaces. And in terms of the stated goal, obviously, we were successful in achieving local elimination in Victoria, at least for a period of time until, with a number of incursions during 2021. Obviously, the success of this policy overall and this approach overall is probably one for historians to judge in the future. But it was a long time, having lived through it as well as probably many of you. And the idea was that after the numbers had come down, there was this need to relax restrictions to make it sustainable. So the considerations at this point was, what is it that could we start easing? We really wanted to start with the lowest risk activities first, the ones that really were, causing difficulties in the population with, being sustainable. If the timing of easing was felt to be important, if there was easing off too early, then I think it was pretty evident that there was this risk that we might lose control. But equally, on the other side of it, there was this need to maintain social license. That we can't do things that aren't acceptable to the population. And so into that comes concepts like proportionality, the burden of disease and the burden of control. So on who bears these burdens of lockdowns, and then some of those broader impacts on society of lockdowns. So the questions really that needed to be answered were, what public health and social measures could we relax first, and then at what time could we go back to a new normal without risking resurgence. And so there were two models that were used to inform this decision. The first was from Jason Thompson's group at the University of Melbourne. And this early modelling suggested that it really was dependent on how many cases were out there in the community. That if there were too many cases out in the community, the chance that one of those people would set off an outbreak was much more likely than if we waited a little bit further till there was a lower case number, and then the risk of a resurgence after that was felt to be much lower. So this is sort of the simplified version that was presented publicly. And on the website, and this was also public, was some of the how this looked behind the scenes. So what was done was this microsimulation approach, where there were different runs, and then you could see that if there was a fewer number of cases in the community, and then there was a relaxation, that there's a much lower chance that there would be a loss of control, and then the need to reimpose restrictions. What the model did do also well was to specify all the things that we didn't know, and all the limitations to the model. So in this model, they weren't really able to take into account unknown source cases, for example, which might be really important. And so that was something that we had to consider when we were putting all this together. The Burnett, so led by Margaret Hillard and Nick Scott, also had similar findings, thankfully. This model was commissioned as well, and what we were really looking to see was when there was a different approach, did they come up with similar answers, and thankfully they did. And what they found was that if there was an early reopening, that there was a very high chance that there would need to be a reimposition of restrictions, and there'd be a loss of control. But if it was delayed a little until there were a lower number of cases, then there was a much smaller chance of a loss of control. And the way this was modelled was quite different to the way that Jason Thompson's model worked. They could model different settings and different restrictions differently, and could calibrate this to some extent with what had been seen up to August, and then could model out different choices that we might make after that. So there were lots of issues in this, and the main one for policymakers was consistency. So, why can't I gather in church when I can gather in a pub? And why can't I do this when I can't do that? This becomes a real issue, and it always becomes an issue when you're trying to explain this to the public. The other thing is that it is quite difficult to unpick, what is the impact of individual interventions, and that's important for modellers, because they need to be able to put something into their model to say this is the expected effect of a curfew or density quotients in a particular setting, but we don't really know that for sure, and sometimes we may have to make educated guesses about that. And then when we're trying to, think of the worth of an individual intervention like a curfew, how important is that really? We don't know, but we do know as part of a package it did seem to it was associated with a reduction in interaction, and therefore a reduction in presumably a reduction in transmission. The other thing is everyone thinks their workplace activity is low risk, and I can't tell you how many times someone told me that they hadn't had a transmission in X setting, and why are we subject to restrictions? But obviously there's this public health paradox where everyone is shut down, so of course there's not going to be any cases in those settings, and so the cases averted isn't really something that you can easily measure, at least in reality, but you can do it in modelling. And then the other thing is that it is quite easy often to pick holes in modelling. All models are wrong, and they're all simplifications of reality. And that's often very difficult to explain to the public is, why didn't you consider, whether architects can go back to work or not? Why isn't my group modelled explicitly? But that's not really necessary when you're making these broad policies. So fast forward to 2021, and again, this is modelling that I haven't been involved with, and just noting that this was modelling done by the Burnett, so Nick Scott and Margaret Hillard's group, and released in September. So, when obviously it isn't really fair to judge, how this model has turned out in the context of Omicron and all the other changes that have happened since then, because that certainly wasn't known at that time, and you can see the black line there was the data that they were working with in terms of trying to predict what might happen in the future, or at least model what might happen in the future. So the purpose of this was really to, explore some of the potential impacts of different ways that there might be reopening in the context of increasing vaccination coverage. And their main findings then was that there was a risk of that hospital capacity might be exceeded, that if there was more testing and identification of more cases, and that might reduce the peak, and also broad settings that might reduce non-household transmission that occurred outside the household, might reduce that peak as well. But they did note a very long list of uncertainties that might have increased or decreased the number of cases that they modelled. I think there was a lot of common misconceptions. When you draw a very dark line in the middle of a graph, then people expect that that's what will happen, and it isn't. Just to reinforce, this is not a forecast. This is a this is a scenario modelling, and so the misinterpretations that you read is we could see or we expect to see 4,000 cases a day in December or January. We expect to see 2,000. We almost certainly will not see that amount, because we put policies into place, that there are uncertainties in all the various parameters. So the way that perhaps that we might read this would be to say there's going to be a lot of cases to start with, and so that might be a signal and need to tighten some of the restrictions we have, or to ratchet up some of the control measures and some of those levers that we have. There is this huge variation between best and worst case scenarios. So, if we just look in terms of cases, it is possible that there might be 10,000 cases, but equally it's possible there might be only 1,000 cases a day. And obviously what will probably happen is somewhere in between that. In terms of me looking at this from a hospital point of view, I think, we would need to have an operational plan for, up to 100,000 cases, being 10,000 cases a day, and they sort of need to be looked after for about 10 days. 4,000 people in hospital, and around 800 up to 800 people in intensive care. But also you can see that there's a ratio between new diagnoses, hospitalisations, and intensive care, and obviously that's a parameter that could very well be impacted on by vaccination. And in September, October, we didn't know exactly how effective the vaccine was going to be, and a main driver of hospitalisation is length of stay. So that's a key uncertainty here. So watching that ratio between the number of new diagnoses a day and the number of people in hospital is actually quite an important thing, and that will tell you very early whether things are going to plan, or things are getting worse or better. And so how has this model performed? And again, this is not to say that, there were things that could have been anticipated in September that we turned out to have. And obviously, one of the big changes was the onset of the Omicron variant in early December. On the left is the graph that is roughly to scale, the same scale. So you can see that the number of cases is much more than we had expected. The graph on the right is not to scale because it's very difficult to do that, but you can see that the number of hospitalisations is much lower than expected, and that reflects the reduced severity of the Omicron variant, thankfully. So where are we at the moment? So obviously Omicron has come in. Previous infection and vaccination look like they provide limited protection against infection, although they may provide a little bit more protection against severe disease. And overall, this does seem to be considerably less severe than the Delta variant and strains before that. It is a little bit hard at the moment to work out exactly where we are. There's a lot of under-ascertainment of cases because of saturation of the testing system. People are clearly put off by delayed results. There's now rapid antigen testing, and we're not entirely sure how many people are testing positive with a rapid antigen test, and presumably not everyone is registering their positive test in the system. And clearly it's also hard to get your hands on a rapid antigen test at the moment, so there are probably infections in the community that are not going diagnosed. And then the demographics of cases is changing, and again, how much under ascertainment might there be in different age groups is always going to be difficult to know. So what we find ourselves in is these, these pillars of control that we have, public health and social measures, vaccination, the TTIQ system, are all being challenged by high case numbers, by, at the moment, in late December, we're sort of in this place between, all the events of Christmas and New Year, and then the resumption of school and work in late January. And then vaccination, we think boosters will restore protection to some degree, but how long that protection will last for is not clear at this stage. So in terms of policy and what does the community want? They want consistent policy. They want some clarity and some rationale behind it to make it justifiable as to why they're doing things. They want some transparency to say, who's given this advice and what have they said, and where has all this, who's advising government and do they know what they're talking about? The public generally expect, competence in the sense that, they don't really care, what all those issues are. They just want a rat test. No amount of excuses will, is going to stop that criticism. They want, and they want fairness. That they want equity. That not an unfair burden of restrictions or interventions on a particular group in the community. So where does modelling fit into all this? So modelling is really, there's lots of different uses, and I think Jody will have spoken about this. But in terms of policy making, what it is best at is, what if questions. What if I do? What if I release restrictions early? What if I release them early, but keep that sort of first stage on for longer? You can explore some of these things without actually having to live them. And that even though that's no guarantee that things will work out as planned, it gives you the best chance that your policy will be successful. You need to be very careful about when you're looking at models that are you really looking at them in a qualitative sense or in a quantitative sense? So particularly with the Burnett model, for example, I would say that the way I would read that is to say, I expect hospitalisations to go up in December, January, rather than saying that I think it will be 4,000 cases in hospital on this date. So, there's this sort of broad feeling you get rather than an actual number that you pull out of it. And there is this issue that, when you give someone a number, they sort of hang on to that and say, look, this is the number I'm planning for, and that's very much not the best way to look at models. The models need to be fit for purpose, but on the other side of it, they just need to be just complex enough to capture the main processes. So we don't need to model, what is the effect of bringing architects back into their office. We can assume that they're probably broadly similar to other office workers, for example. You need to make these simplifying observations so that you can have a process that's tractable. You need to make explicit assumptions and sensitivity analyses where it's appropriate, and I think both Jason Thompson's model and Margaret Hillard and Nick Scott's model did that very well, where they had a whole page of what are the things they don't know that could make quite a difference. Unfortunately, they aren't always read, but those pages aren't always read, but they are important to document. And ultimately, in general, you're probably more confident in what models might show if models using different approaches broadly agree, and thankfully that's what we found with the Burnett model and the University of Melbourne model in trying to inform the Victorian roadmap policy. What does government want from modelling? Well, the first thing is they want a clear answer, or at least some options for what they can do. They want things that you can actually do, implementable policy, realistic scenarios and interventions. It needs to be timely, so an imperfect model, a day before you make the decision is much, much better than, a perfect model delivered a week after you've made your decision or you've needed to make the decision. There is a lot of trust in this process. The worst thing is about trying to leaking of decisions that aren't yet made. And so, often governments will go to groups that they've worked with before that have been shown to be reliable and are experienced. They want an output, a graph, something that can be communicated to a variety of stakeholders, so not just the public, but you need to explain this to politicians and to other experts in the area. And then you need to consider the relevant factors. And obviously, this is determined by the terms of reference. But what is the impact on disease? Have you thought about equity? Have you thought about cost? If that's a question that's relevant. And then ultimately, you want methodology that's robust enough that can be defended in the court of public opinion, and then making sure that any uncertainties are spelled out so that those gaps can be closed later on if more information becomes available. So it is important to note that this is probably actually the order that government would look at some of these models in terms of academia. We often look at it the other way around. So robust methodology is probably the most important thing for academics. Timely provision of advice probably isn't quite so high up on that list. You publish a paper when you get round to it. What government wants is often quite different to what policymakers need. So I'm neither a policymaker or a modeller, and so these are the questions that I might pose for the future and how this all might work for perhaps the next pandemic. Is models often rely on a lot of data, and the more data that can be used brought to bear to parameterize these models is really valuable. So how can we provide this data to people that need it, but while ensuring that there's appropriate governance and oversight, and most importantly, the interpretation of this data is correct. What models are there out there? There's probably I know of probably at least half a dozen modelling groups out there. Which ones are good, which ones aren't? This isn't probably immediately obvious to policymakers. And what questions do they answer, or can they answer that might be relevant to decisions that might be coming up? How do we balance the need for timely advice with some sort of rigour and transparency and oversight? How can we better anticipate what other questions are about to come up to give people enough time to get things into line and to make models that will answer questions? And then how can we best integrate advice from different discipline areas? So modelling is only one input into decisions, but there's sociological data and surveys and other things that are important. It's not important to inform the decision, but it's also important to inform each other's areas. And then how do we best communicate all of this to stakeholders? So I'm going to finish there and just end with some acknowledgements of modelling groups that I've spoken to, and then to the Victorian Department of Health for their support when I was working there. Thanks very much.
Jennifer, Patricia and Alan, thank you for 3 fabulous talks. We do have time for discussion and questions. Jennifer, I was going to start with you and to hear more about T cell responses, but particularly in the elderly or in compromised groups. Do you have any data on that?
We don't have data on that ourselves, but there's been a lot of interest in this, of course, and I think it's a really interesting area. I mentioned briefly, someone else asked about that in the Q&A. In general, the data that exists suggests that there are slightly lower both T and B cell responses, particularly in elderly individuals compared to their younger counterparts. And I think it's quite an interesting area of investigation. So there's been work both now in COVID and also influenza looking at the response to vaccination in older age groups. And there seems to be this impact of what we call inflammaging. So this baseline inflammation that increases with age. And there's a lot of increasing evidence now that suggests that that can affect the impact of a vaccine, and that basal inflammation can actually change the T cell response, and then that maybe hinders the antibody response to the vaccine as well. So I think we're going to see more research into that area, and also it'll be interesting to see with boosters, because of course older individuals might be the populations where we want to give additional vaccine boosters down the line to maintain their levels of protection. And there'll be interesting opportunities there to understand how the T cell response to those boosters compares in different age groups.
Apart from boosters, are there ways that I can keep my aging T cells competent and young?
That's a really good question. I don't know that we're fully there yet. I'm not going to tell you to load up on anti-inflammatories necessarily. I think there's a lot of work into understanding chronic infections. I think CMV and other viruses and how that impacts our T cell compartments as we age. But I think we're still a little bit further away from understanding how we can modulate that. But it'll be good to see, maybe we can use different adjuvants with different vaccines, and we might be able to modify vaccines that way for different age groups. So the future is interesting, but for now we might just have to watch.
Your data about the subjects who were previously vaccinated and then had a natural infection, and the delay in both the antibody and presumably T cell responses, it was almost as though they had to get sick before they could get better. They had to be symptomatic. They had to suffer. Are there explanations for this? Does it relate to the dose of virus? With a vaccination, are we giving 10 times the amount of antigen that natural infection delivers? Are there other explanations?
Yeah, we were quite surprised by that delay, perhaps a bit naively at first, but it wasn't what we were expecting to see. I think there could be a few factors playing in. One, when we give a vaccine, it is a really coordinated burst of a lot of antigen that we know goes to a lymph node and should kick everything off. I think one of the biggest caveats to our study there was that we were sampling the blood. And so we didn't have data on what kind of immune responses were being recalled in the respiratory tract or at mucosal surfaces. There's been some interesting data from non-human primate studies where they showed that the immune response in the nasal mucosa and in the bowel and in the lung happens much faster than what they saw systemically. So it is possible that we were just getting a bit of a delay in what we saw in the circulation. I think there's also going to be differences, related to viral load, viral replication, and how that virus that, comes in through your respiratory tract gets to a lymph node, and then the timing of how that is actually presented to the immune system. So there's a few factors there, but I think trying to understand the local tissue immune response would be really interesting in those cases of breakthroughs.
And do you have methods that you can do that? Can you take nasal swabs and look at epithelial cells and so on?
Yeah, so we have sampled their saliva actually, which seems to be a pretty convenient way of tracking antibody responses. So we're doing that analysis now. And there have been some groups that had good success actually using nasal swabs to collect immune cells and looking at some of the local T and B cell responses. So that would be a really nice complement, I think, in the future studies.
Thank you. Trish, your presentation was so clear that there weren't any questions apart from are you available for the next meeting to present again. But if modelling can be made so clear, why don't we use modelers to explain it to the public? And I might ask Alan to comment on this as well, because there appears to be a disconnect between what's generated in models and what the public actually understands.
I think it would be really great if we could get that understanding across to members of the public. It is something that people have to be willing to want to understand, though. I think that's probably the first step, and some people will just discount modelling. There has been, through the Doherty modelling, I'm sure you may well have been aware, with the large press conferences at a national level where Professor Jodie McVernon was delivering the modelling to explain it. But I think it is this background that people need to actually firstly understand what goes into the models. And one of the things I guess that I would really like to get across to the general public is that modelling COVID is a moving feast. Like we don't, there's so much that we don't know and so much that's changing. And I really liked, Alan, how with your presentation, you really reinforced that, it's to ask what if questions rather than predicting. And I saw in the Q&A, there was a question about, are there any good models that have been used for forecasting? And I think it's just really important to bear in mind that we're not forecasting really, we're answering what if questions, which are different to forecasting. When we forecast, we generally have a really good idea about what the drivers of a disease in a population are and what the factors are. But with COVID, we just don't yet have that. So we just have to keep answering these what if questions. And I'd love to just do a primer for the general public and let them understand what modelling is.
Before we get to Alan on what government might allow the public to hear, Trish, what feedback occurs back into the model? So with COVID, Omicron clearly is behaving differently from Delta, at least at a hospital level. There appears to be less pneumonitis, but nonetheless, patients are sick and they don't recover quickly and they lie around for a long time. Is that sort of information fed back into the model as a feedback loop?
Look, I think that overall, the team that's done the Doherty modelling, and I really can only talk about the Doherty modelling, I guess, is very multidisciplinary. So it's got social scientists, it's got clinicians. So we are getting that information all the time, as well as reviewing constantly what's happening overseas and what's being observed in different settings. One of the questions, though, is, when we see, for example, what happened in South Africa with Omicron, what parts of that are going to replicate in Australia? Settings have different immune profiles and things like that. So we do need to gather that information from everybody. And so we consult very widely and build those changes into the models. They're ever changing.
Thank you. Alan, you've got a question, and then there are lots of questions for you.
Right, no worries. My question is actually for Jennifer, and we did have a little offline chat. I'm just wondering, we do serosurveys. We've basically lost track of how many people have got infection, and serosurveys are one really helpful way to define, what proportion of the population have either been vaccinated or had infection, if we do in serology. Just wondering if there are sort of, similar things that could be done in a high throughput way for T cell responses, given that T cell responses are probably going to be more important for protection against severe disease.
Yeah, there absolutely are sort of more standardized assays that we could use for screening just for the presence of T cell responses. And there's been some nice work, particularly by groups out of the US, that have defined different T cell targets that can be used to differentiate vaccination from infection. Additionally, there's been some interest in just T cell repertoire sequencing, so just taking bulk blood samples and looking for evidence of expansion of specific TCR sequences that indicate infection. So it's definitely plausible. I think everyone always thinks of T cells second to the antibody responses, of course, but it's certainly doable, I think, with a little bit of forethought and specificity for the infection versus vaccination situation.
You know, it almost is a sort of chicken and egg thing. You know, you can measure humoral immunity so much easier, so that becomes what everyone thinks about. But there aren't, you know, T cells are probably quite important and will probably become increasingly important as time goes on. So,
and I think our data at least is encouraging in the sense that we see, you know, the memory T cell populations being maintained, and that sort of, I was quite struck by that stability between, you know, 6 months and 15 months in our follow-up cohort, where frequencies of those memory T cells really weren't changing. So it remains to be seen if those cells are as long-lived as what we saw with SARS-1 survivors, but they certainly do seem to be sticking around.
Thanks.
Alan, you had a slide, issues encountered with modelling, and was that your experience? Was the feedback coming from government or within the health department, or was the feedback coming from members of the public?
Oh, it comes from everyone, really. I mean, government asks these questions, you know, in cabinet, in private, and they will ask, you know, well, how sure are you about the modelling, and what about this, what about that, and you know, obviously governments aren't mathematicians or professional modelers, so they will ask pretty much, you know, some very similar questions to how the public will see it. But when it comes out in the public arena, often it has that, you know, political lens about it. Just, you know, there will be people that will just want to pick holes in anything, and you know, you'd sort of need to see through that noise. That's not to say that there aren't valid criticisms of modelling, and that was sort of some of the motivation to try and get two groups to do, you know, answer the same question. Obviously, there would have been the issue that if they hadn't come up with the same answer, we would have to work out what to do still. But you know, that's where having that approach does help to some extent, at least, and that was in the Victorian context at that time. There are downsides to doing that, so you know, it's twice the work to engage with two groups, and you know, you need to make sure that they actually do have the same settings, and I think this goes to, I think, that question that you had for Trish about you know, modelers explaining, and obviously Jodie does a fantastic job at explaining modelling, and yeah, and Margaret Hillard and Nick Scott from Burnett do as well, and Jason Thompson did for that modelling. But there is a universe of things that you can possibly, you know, that you can model. It's what is the policy relevant question, and what is implementable policy that comes out of it, that I think is important. And I think all the modelers do a very good job at sort of sticking to their patch and explaining modelling without saying, well, this, you know, that means we can do this or we can't do that. That, because that properly is a decision for government to make.
Trish, if modelling is going to be made public and accessible to the public, does it need to be differentiated from forecasting? Because the public might think of it as the Weather Bureau. And what other analogy would you use apart from the weather?
I guess people, when they think about models, they do think about weather, and you know, we can forecast the weather. So I guess where the term forecast come from, and we can forecast things like each year we forecast influenza and try to forecast like when our peak is going to come, and that's based on our prior experience of influenza in Australia. So I think the really important message to get across is we sort of tend to call it, you know, scenario modelling or something like that rather than forecasting. So we probably need to change the language itself. It's more, I suppose, you know, if you had 3 buttons and you're going to push them, what's going to happen if I press this one, or what's going to happen if I press this one? You're not, it's more like that. And I think that that's maybe what we could explain it as. I can't really think of a real life situation that we might do, but I mean, there's lots of things that we could model. We model vaccination all the time for other diseases, and say what would happen if we could introduce vaccination at 60% coverage, or what if we could do it at 70% coverage. We've been doing that for diseases for a very long time. So it's not unusual to be doing it for COVID.
Trish, thank you. Jennifer, there are a couple of quick questions about T cell responses in pregnant populations and also Cd8 data in breakthrough infections.
Yeah, so some of the groups at the Doherty have been quite keen to look at responses in pregnancy. And in general, what they found was that there were not substantial differences to the immune response to infection in pregnancy, but that there were some differences in activation of innate immune cells and unconventional T cells like gamma delta T cells in the pregnant women. So the differences actually weren't so much where we thought they might be, but more in that sort of innate side of things, potentially related to pregnancy changes. And for the question about CD8s, we did have Cd8 T cell data in the breakthrough study, and it was quite similar to the CD4s. So again, we didn't see a lot of recall, and it tracked quite nicely with the CD4 responses. So everything seemed to go in concert together there.
Thank you. And Helen and Trish, what does modelling show about Omicron getting back to baseline rate? Ground zero.
Yeah, look, it's difficult to know. I mean, clearly it's on the downslope, and both boosters and a whole bunch of people getting infection probably contribute to that to a large extent. I think and Trish probably has a finger on the pulse a bit more than me, but it will probably decline over a little bit. I think the forecast, at least in Victoria, is that it'll flatten out because of resumption of work and school, but may not increase too much. And then I think the next big wildcard coming along is winter, but weather and how seasonal it is probably important.
Yeah, I think that's really important, Alan. And I think also one of the lessons that we need to learn is, are we going to see circulation of multiple variants at the same time, and how's that going to work? You know, is that going to be the pattern that it settles into? Like, we do have other diseases where we see multiple versions circulating at the same time, and that modelling becomes much more complex when we start thinking about how immunity works and protection from one strain versus another. But hopefully Omicron, we've kicked it out the door.
There is that, difficult immunology that Delta doesn't protect against Omicron, but Omicron might protect against Delta, and that would do your head in, I think. If you try and model it.
So, Alan, while your head's being done in, there's a question about whether politicians interpret scientific and technical data differently from other people.
Look, I mean, politicians are like, they're representative of the general public. My experience of them is they're pretty intelligent, and we do spend a lot of time explaining it to them. So, unlike a press conference where you have an hour or two to try and explain everything to a wide audience, you can spend a very long time talking to politicians about modelling and what they do and don't show and their limitations and so on. But in the end, it is a pretty difficult concept to explain, and it's very important to have key message. When you're talking to politicians, you have key message to say, well, this is what I want you to take away from it, and this is what I don't want you to take away from this modelling. So I don't want you to say that there's 4,000 people in hospital in December, because what I do want you to say is, or this is how I interpret this modelling. And so politicians are pretty good at messaging, and they're pretty good at sort of distilling relatively complex situational analysis and analyses for the public. They don't always get it perfectly right, but neither do I. So it's part of a process, I think.
Alan, thank you. In the last couple of minutes, I'll put each of you on the spot and just ask, what question about Omicron would you like answered in the next 12 months? Jennifer, starting with you. What would you like to either answer yourself or pick up in Science or Nature and see that someone's answered for you?
I think the big question right now, and it can't really be answered until we understand what the next variant coming is going to be, is a better understanding of what kind of immunity people are going to be left with after they've had presumably a couple of vaccines and an Omicron breakthrough infection. I think that's really the question of the hour. You know, how cross-reactive is that immune response going to be? How well protected are they going to be from what's come before? But what we don't know is what's going to come next, and is it going to be related to Omicron? Will people have broader immunity, or are we going to be starting again, you know, from variant to variant? And I think that's going to influence where we have to go with vaccines and boosters and what kind of waves we're seeing in the future. So I'm keen to see that.
Thank you. Trish, your wish?
I would really like to know how many people have actually already been infected with Omicron. That would certainly make our life as modelers a lot easier. We have to, at the moment, sort of rely previously where we had, you know, quite a good handle on how many people were getting infected. Now we really probably have to backtrack from hospitalizations and looking at our infection to hospitalization rate in reverse to try to estimate how many infections actually occurred. So for me, that would be, you know, a serosurvey where we can separate out vaccinated versus infected people would be fantastic.
Terrific, thank you. And Alan?
For me, I think it's the big social questions about we're at a very different spot. Everyone, almost everyone's vaccinated, and probably, I don't know, maybe a third of people have had infection. Omicron does appear to be less virulent, but there's no guarantee that the next variant won't be worse. I guess that my question is really, what is that package of public health and social measures, isolation and TTIQ and vaccination and future, thinking about future vaccine strategy when booster effects wear off. What is that package that has social license and we can keep, minimize all the burdens on society? We've been through a very difficult couple of years, and I don't think anyone wants to go back to any of that again. But what can we do to stop the emergence of something nastier but while keeping society going and minimizing the burden on people?
Thank you. Three terrific wishes. I hope they come true. I want to thank you for a wonderful discussion and very strong presentations.